I think we are live. So,
Perfect.
hi guys, welcome to another episode of Z.I.P Talks. Today we're joined by FTC team RoboKings Aurum from Australia. My name is Arnav.
My name is Shreya. I'm from Team Z.I.P Ties.
And my name is Shishti.
My name's Tinko, this is Zane, and this is Raf. And we're all going to be part of the upcoming 12993 for the Into the Deep season.
Awesome. So, I think we can just sort of get started. Do you guys want to give a quick rundown of your robot, and then we can ask more in-depth questions?
Of course. So on our robot, we knew immediately from the start of the season that we wanted to have an autofocus robot, and that linear slides will have more consistent, more reliable, and also quicker motion than any robot, because you won't have as much issues with odometry drift on your slides extending. So we have two main extensions on our past season's robot. We have 5 stages of intake extension on Masumi slides, and then 4 stages of outtake extension, which we've also pitched so that when we're, especially for auto, and when we're filling up pixels on the lower area of the backdrop, we can have to drive less. On our intake, we have an active intake where pixels come into our chute, where with color sensors, we detect when pixels are in our chute. Our chute comes up and into the middle of our robot, and we transfer vertically by grabbing the pixels and pulling them out with our claw. Then our claw comes out to the backdrop, and we have our pitch degree of freedom, our turret degree of freedom, 2 horizontal stages of MGen 7 linear rails, and our arm and claw pivot. Finally, we have our drone. Our drone launcher is a very simple drone launcher. We just use bungee cord and a screw to mount on the back of the drone. And then our climb is power shared with our pitch. So when we raise our pitch past a certain point, we have wedges that release our climb, and then we have string attached from our climb to our actual pitch. When we pitch down with our 40 RPM pitch motor, our climb lowers. That's a really brief overview of the robot. If I was to go through everything in detail, it would take an extremely long time, but feel free to ask any questions.
Yeah, so I've seen your behind the bot video and everything, and you guys have an extremely complex robot. From the beginning of the season, how did you guys sort of come up with these ideas, the pitching, outtake, the horizontal movement on your claw, just really sort of next level ideas? How do you guys come up with these?
Well, once again, that is kind of a design philosophy. So from the very beginning of the season, we wanted to design we were looking towards the World Championships. We wanted to design a robot that would have an extremely high scoring and hopefully consistent auto that would work well with other teams, and then also be able to do everything in teleop period. Basically, we wanted to push the limits of what an FTC robot can do. And while we may not have done that in consistency, we think we have certainly done that in design. So like we mentioned before, the linear extension on our 5 stages of intake slides and our pitching outtake slides means that for our autonomous, we have to drive less, which means that we're able to do cycles faster. For our horizontal extension on the outtake, we knew from the very beginning of the season that we wanted to have some form of horizontal extension, because when you're doing autonomouses with other teams, having the ability to score over the top of them means that you can have 2 high-scoring autonomouses working together. Also, we can use it to help correct any positions with cameras on the back of our robot. So for our yellow pixel, if we look up from the April tags and we see there's a yellow pixel in the left slot, we can use our rail to adjust rather than our whole robot. And it's also very useful for teleop, once again, for scoring over other teams. So just looking at basically what you want the robot to be able to do. So the amount of cycles you want the robot to be able to score in autonomous and how you want it to look working with other teams, and then finding subsystems that will work to meet those goals is probably how we do it.
Yeah, so I see you guys are calling a lot of hardware, and in order to have an accurate auto, there's often a lot of issues with sample rates and sort of keeping this fast. How do you guys ensure that you guys have fast loop times in order to ensure that all your sensors are updated?
Well, obviously, with this robot, the first challenge was already just making stuff work together. We have so many degrees of freedom on the outtake. Everything has to work. There is a very small timing between every part of our finite state machines. But the biggest challenge we had during words, preparing for words, was actually what you said, trying to optimize our loop times. We spent a lot of times being sure that were able to cache all of the hardware calls that were done to motors and everything. We did a bunch of optimizations regarding code. So on the backdrop, we have a whole set of inverse kinematics that allows us to always move along the backdrop. So even if the robot heading turns and the robot moves around, the position on the backdrop stays the same. We also wanted to we used a lot of sensors, as Tinko said. So color sensors and a distance sensor on our claw. And those are I2C objects, so they take a little bit of a while to do their hardware calls. So we did a custom way of calling these objects on an interval. So we have a periodic supplier. It doesn't call out this, it isn't continually calling out every single loop the calls from the distance sensor or the color sensor. That means that during a 100 millisecond time interval, we call our loop or I2C devices only once. We also structured our code so we could read at the start of every loop. So at the start of the loop, we read every single hardware device during a cache bulk read. So everything's cached with bulk read, and we say if we're on this state of the tally up or the auto, we want to read some devices or like just one of the hubs or just the other one. So that also allowed us to minimize our loop times to around 14 to 20 milliseconds, which is average loop time for a FTC robot. On this robot, it's very impressive that we were able to actually do this.
Yeah, I really like the strategy you were talking about. It's kind of like a mix of like bulk read as well as like I've seen a lot of teams use like priority queue as well. Yeah, that's really interesting. I think there are a couple hardware questions we have as well.
Um, yeah, I mean, obviously, like, sort of blending hardware and software. When you guys like work on your game strategy, how do you make sure that like with all these complex controls, with your horizontal sort of extension on your slides, your outtake, as well as like all your complex features on your intake, how do you make sure that the drivers have the ability to like perform the robot as best as they can?
So I feel that part of it is, as I talk, like trying to optimize controls and like just having them as simple as possible. So one thing we did on code, and going back a little bit to loop times, because of the linear rail and it's on a reel, because of it, when you move the servo a little bit, it ends up moving it by a lot. So we realized that if we just put in the controls normally, if the loop time was high or low, that would make a great variance on the amount of the rail would move. So we did it in a way that it kind of caps on the loop time. So it doesn't really matter if the loop time is 25 mils or 300, it will always move the same amount per loop at maximum. That increased the consistency on the drivers. The inverse kinematics was also good, but I feel that one of our drivers can talk about how actually driving it was a better experience.
Another thing that we've done is we've automated a lot of processes. So in regards to the actual intake, transfer, bringing our outtake slides out and dropping, that's all one button being pressed 4 times in the same sequence. With all of our outtake degrees of freedom, we've actually we've used inverse kinematics so that when a secondary driver moves a joystick, the entire outtake will move up and down and along the backdrop with everything pitching automatically so that it's working in one plane. So a lot of automation like that, but mostly it's just a lot of driver practice. Driver practice is definitely one of the most important things in FTC. We personally, this season, did not get enough of it leading up to Worlds, and it did show in our performance. So past just optimizing your robot, spending more time driving it, finding out what breaks in a match is probably the best way to get a consistently working robot.
Yeah, I mean, definitely driver practice is a big thing that I think I know our team and I feel a lot of other teams also struggle with. Like, you're trying to add that last robot tweak that last programming fix, and like it goes to the very end, like right before competition, and it's hard to work with that. So how do you guys like sort of space out your season? Like in the beginning, is it mainly just like prototyping with designs, and then as you move on, it's sort of just like refining them slightly, or do you guys have a different sort of approach?
Our season timeline, especially, is I think a little unique compared to most teams, just because of where we're based and where we're our region. We actually have 3 competitions a season: our regional championships, our national championships, and then worlds. So our first regional competition is actually at the very, very beginning of November. Our nationals is at the very, very beginning of December, and we have no competitions from then to worlds. That does have benefits and also some disadvantages. So we don't really have as much time at the beginning of the season to spend prototyping. We kind of need to have a design finalized in the first 3 weeks that we can build for regionals so that we can advance. From regionals to nationals, we just try and optimize that design. And then once our nationals competition is over, if we have managed to qualify for worlds, we kind of take a look at what happened, what worked at nationals, what didn't work at nationals, and how we needed to improve our robot to meet our goals. So most of the first 3 weeks of the season for us is probably designing. We try and have a fully designed robot by the end of those 3 weeks. Leading up to regionals, we build, reiterate, or see our intake. If it doesn't work, we'll redesign a new one. From regionals, we'll usually make minimal changes to our robot from regionals to nationals because we only have a 5-week turnaround, and then it's only after nationals that we have 4 months and summer holidays to properly look at our design. So we don't have competitions every month like some of the US teams do.
Yeah, that seems like a super tight schedule, especially in the beginning. I feel like that early season time is like the most critical, right? That's where you get all the time to test out ideas, but it seems like you guys have it cut super short. But like you guys did amazing at World, so like something must have worked. So for your like linear slides, I know one problem that we often face is like the stringing gets caught. So like how do you guys fix that with like your inserts? And then also I remember seeing in like a behind the bot video that you guys countersprung your slides. How exactly does that work?
Okay, yeah. So we actually have had no stringing issues in regards to string getting stuck. The only stringing issue we've had all season was at Worlds, our return string snapped, which wasn't touching any bearings, but that was not during a game, fortunately for us. We actually use, I don't know if you can see it very well, but we use vertical inserts. So I'll try and bring you closer. Our bearings are actually mounted vertically, and if you can see in our mounting here, there's absolutely no space for our string to come off the bearing. So what we've done is we have a plate, and then we have a 0.2 millimeter shim, our bearing, another 0.2 millimeter shim, and then another plate printed on and screwed together. So for our inserts, there is literally no room at all for the string to come off. We use vertical inserts so that we can have a 2 millimeter gap between each of our slides, which is probably one of the thinnest inserts possible that you can have with the Rev V bearings. But we only do that out of necessity. It's not the vertical insert aspect is because we did not have the space to fit our outtake in if we didn't have them. So you don't necessarily need vertical inserts, but making sure that there's no room for your string to come off is definitely how we don't have any catching, because the string is 0.5 millimeters thick and the gaps are 0.2 millimeters thick. So it's never going to get caught. In regards to counterspringing, we have a non-linear counterspringing method. So we actually have, I don't know if you can see here, but one of our slides, so this side of our slides is strung with continuous stringing. So there's one string going up through the bearings to the top, and then a return string that pulls it back down. And then our other side is cascade stringing, where the string goes up and down, and we have 4 separate strings across each of our 4 slide inserts.
Mm-hmm.
Cascade stringing.
No. Yeah, I know how.
Cascade requires more torque. Yeah. On our cascade stringing side, we have an arm, which is just Actobotics beam
Mm-hmm.
that we've attached to a pivoting point of our slides, and we've attached it to the cascading stringing. So basically, when the arm pulls down, the slides come up. And what we've done is we've put probably 200 rubber bands in here from our arm, pulling it down. And so the way that works, the way that it's a linear counterspringing method is when our slides are more down, as you can see, the force of the rubber bands is pulling more into the robot because of the vectors. So it's going into the robot and out, so there's not as much force pulling the slides up. Whereas when our slides are fully extended, as you can see, because the arm is out, the rubber bands are pulling it much more this way, which has a stronger effect on the string. So our slides are linearly sprung, and pretty much we've counteracted gravity, so no matter where we hold them, they'll stay. Essentially.
Yeah, that's awesome. How long did it take you guys to like design that, come up with the idea and everything?
Back in power play, our slides weren't going up, so we were just we couldn't afford constant force springs, so we were just playing around with rubber bands. And one of our builders just attached an arm and put some rubber bands on it, and it worked really well, and we've been doing it ever since.
Yeah.
It was completely by chance, to be honest.
It looks super cool though, the way it works.
Thanks. We haven't had any issues with it. And it's really easy to refresh. We just change the rubber bands whenever it stops working.
Yeah, so oh, maybe you can go.
So like on that note, you guys were kind of mentioning about like all these different mechanisms and stuff. Like, how do you guys maintain consistency? You guys also said like you guys try to avoid moving around as much as well. So like, how do you guys sort of mesh that both together?
Well, that was probably our biggest issue at Worlds. The fact that our super complicated robot wasn't really that consistent. Who'd have thought? We do as much as we can to fix our consistency issues, but it's probably mostly just, it's the period of drive practice where you drive the robot as much as possible. The more you drive the robot, the more you can find out what breaks and the more you can find things to fix it. An example of something is we've noticed that because there are so many moving parts, it was really easy for pixels to get stuck in our robot, which obviously would take us out for a whole game. So we have polycarbonate plates, just
every single part.
Yeah, hang on. If you can see, we have polycarbonate flaps like this.
On every single part of the robot. Guarantees no pixels are getting stuck and easily slide out.
Like something like that. See, we basically just chucked pixels into the robot and seen where they get stuck. Bent a piece of polycarb so that it couldn't get stuck and then kept chucking it in. But it's honestly just the repeated testing period and finding out what goes wrong. Slow motion videos, analyzing your performance to fix it is probably the only way to get a consistent robot, which we personally did not do enough of.
Yeah, like we always like, at least on the programming side, we're like a consistent error isn't really an error because you can at least tune for that or like offset that, right?
Yeah.
Like especially in motion for friction, right? Some teams like use feed forwards, and especially like in Worlds, I saw that like motion was like a really big part of this game, especially since there were like ground junctions and whatever. I saw lots of teams were like really on for like odometry and that kind of thing. Like, how do you guys sort of smooth out that motion so it just like glides?
Yeah, localization has been one of the biggest problems in our auto during the season, mainly because there's too much driving and you just go around the truss. If you're trying to do a lot of high cycles, you're going around and curving, doing spline. And on this robot, it's kind of like uneven weight distributed. So it kind of like drifts a lot during auto. So what we did was we worked on a protected relocalization. Odometry is a relative way of relocalizing. So it will always depend on what your robot doing. It doesn't have any absolute correction. So that's what the A protector for. Pretty much every time we do our first cycle, we assume this one had no drift. But every cycle afterwards, we say, hey, look at the A protect, check the difference between what odometry says, correct for what the A protect actually says you are. And that has improved our autos a lot during Worlds. It allowed us to go and change fields and just have the robot consistently splining the paths we wanted
Just as a side note, we use two-wheel odometry
with IMU.
with the IMU, and we use the GoBuilder odometry sensors.
We also
Yeah.
credit IMU for better cycle time.
Yeah, so why do you guys choose to use two-wheel over three-wheel auto?
That's
We never got the three-wheel working.
Oh, okay.
We just had too much drift because of our loop times hardware.
Mhm.
Because of the uneven weight distribution and the way that the three wheel works, because there's two axes on the odometer wheel, there's some micro jittering on it, and because of the uneven weight distribution, that messes up your heading pretty bigly. And because odometry is pretty much all based on heading, if there's the slightest drift on heading, it compounds a lot. So our decision was like, let's use IMU. IMU is absolute. It doesn't drift that much. It has a very slightly drift. So that's what our thought was. It's better to be fully consistent on this than to have a three-wheel auto, which is technically more accurate, but it ended up drifting more on our robot.
Last season, we worked for pretty much a month straight leading up to Worlds power play to try and get three-wheel auto working. It never did. So if it ain't broke, don't fix it.
Yeah.
Two-wheel works for us.
I'm gonna go a little bit back. You guys said that your stringing broke and you did driver practices to see if any parts broke. What would you do if a piece that was important broke during a competition where you didn't have access to parts to fix it?
That will never happen for us because we have a spare plate or a spare part for every single place in our robot.
That's a smart system.
I've seen like lots of teams, like you guys have pretty balanced like hardware and software. I've seen like lots of teams use like modular designs in order to kind of like, work on hardware while software is like tuning. How do you guys like distribute the work during the season so that you guys can get everything done?
Well, essentially our CAD designer, our main CAD designer, he's not here right now, is also our lead software programmer, and then our build team is separate. So our build team works alongside our CAD designer while he designs to build the robot. And then pretty much once the robot's built, he can move on to coding. So with our team dynamic, it just kind of works.
Yeah, so like switching back sort of into the like materials and weight distribution thing, with such like a long pitching arm and then even the horizontal sort of movement, how did you guys like make sure? I know like weight distribution, you guys mentioned you had some problems with that, but how did you make sure that like your center of gravity was low enough so that you don't have robot tipping issues? Because I've seen a few teams, at least in our league, where that's happening.
Of course, yeah.
Yeah, so during that, as you said, we had problems of tipping, and we tried to fix it with code by motion profiling the slides, but onwards we wanted to go again for the full speed, so we decided to fix it more on the building side.
We've spent a lot of time optimizing our weight. We have eight motors and 11 servos. It used to be 12, but we took one off after Worlds, and it still works. We have 8 motors and 11 servos on our robot. 7 out of our 8 motors are on the base of our drivetrain. The only motor that is not on our drivetrain is our intake slides motor, which is still towards the lower end of the robot. In regards to weight distribution, we actually worked from nationals to Worlds to cut 2 kilograms off our robot, so it's now 14 kilograms. Especially on our extending like subsystems, such as our intake and our outtake. So you might be able to see we have carbon fiber plates pretty much everywhere except for the 2 3mm pocketed aluminium inner structural plates where we need the pocketing for wire management, etc. We've, for example, on our outtake, we've pocketed our Masumi slides so that we have saved 100 grams across all 8 stages of the slides by drilling 6.5mm holes, 15mm increments apart down our slides. And we've also used carbon fiber as bracing where possible. For structural parts like axles, we use 8mm diameter carbon fiber tubing. For our MGen rails, they are MGen 7, so they're pretty much the lightest possible ones that we could have while still maintaining strength. Being really careful about adding unnecessary weight, so we don't need two structural beams bracing our slides together when one doesn't have any wobble issues. But most of our motors are all on the bottom of our drive base. Our battery is in the bottom of our drive base. All of our extending subsystems are carbon fiber with as little on them as possible so that we had less weight.
I think one thing I also saw you guys did is you removed the gearboxes from your motors. So like, how has the additional components that you had to add for that, like, has it added a lot more weight or has it like reduced? Has that like how has that helped?
Okay, well, we've actually only removed the gearbox off 2 of our motors, and that wasn't actually a weight saving thing, it was a space thing. With the stringing of our slides, one of our drive base motors went right through the middle of it, and there was no other place to put it to make our robot work. So we just chopped it off and then printed a cover on it. We're using odometry anyway, so we didn't need the encoders. But having bare motors, oh, hang on, you said gearbox, not encoder. Yeah. Never mind. Taking the gearbox off of all of our motors saved about 1.25 kilograms of 7 out of our 8 motors. So the only non-bare motor is our pitching motor, which is it needs to be a 40 RPM motor, so it needs to have a really, really high torque. So we couldn't do that reduction. But it actually wasn't very hard to implement. We used a 2-stage reduction on our drive base. I'll bring you closer so you can see it. So we have our bare motors, and then we use GT2 2mm belts for our first stage of reduction, which have very little slop, and then we use GT2 3mm belts for our second stage of reduction. And we've just used McMaster-Carr pulleys on the actual motor shaft, and then every other pulley is just printed. And as you can see, basically as the wheel moves, the motor moves. We have very little slop, very little friction issues, and 1.25 kilograms saved. So
yeah, that seems I haven't seen like any other team, at least in Florida, do that, so that seems like a really good sort of strategy you guys have going on there. Also, like, I know you mentioned using carbon fiber. How do you guys sort of manage the weight to structural integrity sort of part? Because like FTC is not super physical, it's not super aggressive, but sometimes you do collide with another robot and something that ends up breaking. So how do you guys sort of manage that structure versus weight?
Like we mentioned before, our 2 inner plates are 3mm pocketed aluminium, not carbon fiber. But every outer plate or plate on our intake and outtake is carbon fiber. We've found that 2mm pocketed aluminium, which is what we were previously using because 3mm does not fit in our design, compared to 2mm unpocketed carbon fiber, it's about half the weight and 3 times as rigid, or a third of the weight and twice as rigid. It was one of those 2. So it's actually been an improvement both strength-wise and weight-wise to put carbon fiber on our robot.
Do you guys like have some sort of manufacturing sort of facility to get the carbon fiber, or do you guys like buy it from a company?
We work in a school, so we're very lucky that our manufacturing department likes us, and they have a CNC machine that after 3 years they have very graciously let us use. So we do manufacture our carbon fiber pieces in-house.
That's awesome.
With proper safety protection, of course. Be careful when working with carbon fiber. It's bad for you.
So like kind of traveling back to like the outtake mechanism and like that kind of portion, how did you guys like agree? How did you guys like control all those degrees of freedom?
Yeah, so I mentioned it very briefly before, but we have inverse kinematics and automated movements. So when our slides come out, they will come out and they will come out exactly 1 pixel height above where they were on the previous cycle. When we use our joystick or our trigger buttons to move the outtake, the entire outtake will pitch accordingly so that it stays on the plane of the backdrop. So it's automated and our drivers don't have to worry about that.
On that note, like for driver controls and stuff, I mean, oftentimes we were sort of talking about like how there is often like a lack of driver practice. Like on our part, we try to like separate the buttons as much as we can, or at least like try and keep like related buttons near each other. How do you guys like sort of optimize that and make it easier on the drivers?
For our team, we haven't had as big a need to optimize it like that. Our main driver has been driving on an international level for the past 3 seasons, so he's a really good driver. But we have tried to optimize it by, like we said, our intake, transfer, outtake, and deposit button are all the same button, just pressed 4 times in a row. So we have done things like that to try and keep it simpler. But it's just driver practice. You'll get used to whatever controls there are if you drive a lot with them.
So I know driver practice is definitely a big thing for you guys. How much time do you allot for that before like a match or competition?
It depends on the level of competition. For our regional comps, we'll try and have 3 days. For our national comp, we'll try and have a week. For Worlds, we try and have 2 weeks. Absolutely none of that happened this year. We were building coding autos up until, the middle of the competition. But 2 weeks for Worlds, 1 week for a state, 2 or 3 days for a league meet is what we try and meet. Obviously, that includes, 2 weeks of driving with autos being completed. Obviously, as the autos are being coded, we try and drive for like a month or a month and a half leading up to the bigger competitions.
Also,
but
how do you guys
2 weeks
fund all this? You have like a lot of technology and a lot of components in your robot. Are you guys like completely school funded, or like how do you sort of reach out to companies?
Well, we have a couple of sponsors. I don't have our shirt on right now, but being a school, we have mostly. Sorry, our students going to class.
We have tutorial.
We'll just be late.
Yeah, we're fine.
We have sponsors such as Bosch that sponsor us in tools. So prior to this season, we actually didn't own a drill in our lab. We had a drill bit and a Dremel and a wish.
Sir,
but we've reached out to companies. We attend industry events where basically a whole bunch of manufacturing groups, robotics, STEM-related groups come together. And we're fortunate enough that 2 years ago, we cold emailed a connection and we managed to connect with them. They actually are one of our sponsors. But we just attend all of those events, lots of emails out to everyone. We are majority school funded though, and a lot of our parts have been reused from old seasons. So for all of our bear motors, those are just all of our old yellow jackets that I had to take the gearbox off, and we will reuse them for the next season. We try and keep the cost down as much as possible. Most of our money we bought a lot of Axons this year for our Axon robot because they're really great for power draw. That's all come from the school. And manufacturing is a lot cheaper for us because we do it all in-house with our CNC. So we just have to pay for the cost of the materials. So I think our carbon fiber was probably... No, the carbon fiber we paid for. The carbon fiber was around 350 Australian dollars is what we spent, which is around 250 American dollars. And then we just cut it ourselves and sanded it. We did manage to, if we need materials such as for like our aluminium, we'll reach out to the company that we're buying them from. We'll introduce ourselves. We'll say, oh, this is who we are. This is what we do. Would you be interested in supplying XYZ for free? So that's how we get a lot of our stuff.
So how much did your robot actually cost, and how much did it cost for you throughout the season for outreach events, travel, and just in total?
I think in total this season, the cost to get our entire team to regionals, nationals, and worlds was probably around 55,000 Australian dollars, which is like 30,000 US dollars. We actually, as a team, all of our families individually pay for the travel aspect. It's just the robot that's funded by the school. Sorry to my parents. So I think the robot itself probably has $5,000 worth of parts on it, but the majority of them have been, plate materials have been sponsored, or we're using slides from previous seasons and motors from previous seasons. So I think we've probably spent around $2,000 or $3,000 on robot materials this season.
Yeah, all right. So I think that'll be all right now. Thank you so much, you guys, for joining us. I know you guys have to like go back to class and everything.
We'll be, it's okay.
We even
totally fine
used
to miss it.
to losing classes for robotics.
Thank you so much for having us.
Yeah, thanks for inviting us.
Yeah, thank you so much for joining. I know it's like the middle of the season, and is it summer for you guys or?
Winter. It's freezing right now.
Oh yeah, it's flipped. Okay, well, thank you so much. I think we'll end the stream.
Yep.
Thank
Do you
you,
mind if
guys.
I?
Yeah, thank you so much for
Just know when the
joining.
stream's ended.